Welcome to the HT32 MCU Basic Tutorial, General Purpose Input, Output. Here is an introduction to the chapters in this tutorial. The first chapter is GPIO Overview. Here takes a simple example to introduce the importance of GPIOs in microcontrollers and their applications. The second chapter is GPIO Structure. This chapter helps users to understand the hardware operating principle of the GPIOs. The third chapter is GPIO Modes. Here introduces various GPIO operating modes and the GPIO operation in these modes. The fourth chapter is GPIO Setting and Application. The specific GPIO configuration and an application example are provided to help users to understand the GPIO usage. GPIO Overview. What is GPIO? GPIO stands for General Purpose Input-Output. GPIO is used as a bridge between the MCU and external peripherals. It can be set as an input to receive the input signals from external peripherals, and can be set as an output to send control signals to external peripherals. In the GPIO status figure, the vertical axis is voltage and the horizontal axis is time. The figure is a simple GPIO example. The button function is an input function. It is used to read the external level change of the GPIO. The LED function is an output function. It is used to output the GPIO state to control the LED. The button function level is initially set to high via the internal pull-up resistor. When the button is pressed, the GPIO level of the button changes from high to low, and then the MCU can monitor the I/O level change to implement the related function application. The LED function GPIO is initially set to output high. The MCU changes its GPIO level from high to low to turn on the LED. Before going into more details, we'll first briefly introduce the HT32 GPIO naming. As shown in the examples, A, B, C, D, etc. are GPIO ports and 0 to 15 are the GPIO numbers. When used, the GPIOs usually have the same default mode settings except for some GPIOs that have different default mode settings for specific functions. Taking the HT32F52352 as an example, most of the GPIOs are set to input disable floating mode by default, while some specific pin functions, such as boot and serial wired debug pins, might default to input enable mode with a pull-up. These pins are the PA8, PA9, boot, PA12, SWCLK, and PA13, SWDIO. GPIO Structure. Before entering the GPIO structure introduction, we'll first introduce the terms related to GPIO and their meanings, and the following is the MCU schematic diagram. The MCU pins in the red boxes are also called pads, which can be divided into I/O pads and power pads, etc. In terms of GPIO types, input and output are just two of them. In addition, there are other types of MCU pads, such as VDD domain and backup domain. These types of I/O ports are able to operate stably when the MCU core voltage power domain is not supplied. The VDD/I/O domain type of I/O ports can be independently powered, and the voltage can be different from the VDD. Analog types of I/O ports can provide analog functions, and the final power supply provides power to the MCU. In addition to I/O type, there is also I/O structure, which refers to the internal pin configuration. I/O structures include internal pull-up or pull-down resistors, 3.3 volt or 5 volt tolerant, etc., which determine the I/O structures of the pins in different applications. Finally, output driving is the sink or source current capability when the pin is in output mode, which can be configured. After a basic understanding of the MCU GPIO terminology, let's go on to learn about the internal structure of the MCU GPIO ports. This is a simple GPIO internal structure diagram, including pull-up, pull-down resistors, analog area and digital area, etc. The GPIO pins are used to support the MCU peripheral communication. For basic applications, they can be divided into analog area and digital area. This topic is GPIO, which is mainly used for digital input-output, so we will focus on the GPIO digital function. The GPIO digital function part is shown in this figure. Now we'll explain to you the function that each internal circuit is responsible for. The first circuit contains two protection diodes. It is used to protect the internal circuits from being damaged by excessive voltage. For example, when the external voltage exceeds or falls below the operating range, this circuit can protect the pins and the MCU internal circuits from damage. The second circuit contains a pull-up resistor and a pull-down resistor. When the pin is set to input and there is no external signal, the pull-up or pull-down resistor can stabilize the pin at a high or low level to avoid a floating state and reduce the effect of noise or interference. Next is the input circuit. There is a Schmitt trigger in the input buffer. If the input signal voltage exceeds the high threshold, the input signal will be converted to a high level, vice versa, it will be converted to a low level. This design can effectively avoid the input instability caused by signal fluctuation. Then the signal integrated through the Schmitt trigger will be stored in the data input register. The output circuit is used to output the signal from the data output register. The signal is then output to the output control circuit. Using the PMOS and push-pull mode will generate a high level when the PMOS is turned on to connect to VDD or VDDIO, or a low level when the NMOS is turned on to connect to VSS. Alternate function is used to switch the I/O to peripheral mode. Users can switch the I/O to the supported digital peripheral function, such as I2C, UART, SPI, etc., according to their requirements. The pins that can be switched to other functions are also known as alternative pins, and most of pins are alternative pins. GPIO modes. The GPIO has two modes, the input mode and output mode. The input mode is used to receive external level signals. The output mode is used to output signals to the external peripherals. The GPIO mode can be subdivided depending on the applications. The pull-up and pull-down functions are used in the input mode. If there is no external load, the pin will not be in a floating state due to the pull-up or pull-down resistor. The push-pull and open-drain functions are usually used in the output mode. These modes are introduced following. This is the internal structure of the input mode. When the pin is configured as an input, an external level signal input via the I/O pin passes through the Schmitt trigger, which determines whether the signal exceeds the high or low threshold, VIH or VIL. If the pin is set as an input without setting the pull-up or pull-down function, it will be in an input floating state, and may be affected by input signal noise, causing instability. If the input signal voltage exceeds the high or low threshold, the input signal will be converted to a high level or a low level, and then be stored in the data input register. The pull-up and pull-down functions are used to enable the internal pull-up resistor and pull-down resistor, as shown in the figure. The internal resistors are weak resistors. Taking the HT32F52352 as an example, the internal resistance is about 46 kiloohms. If there is no any external device connected to the I/O pin, when the pull-up function is enabled, the pull-up resistor switch will be on, the I/O will be preset to a high level. When the pull-down function is enabled, the pull-down resistor switch will be on, the I/O will be preset to a low level. When the pull-up and pull-down functions are both enabled, the pull-up function has a higher priority while the pull-down function will be blocked and disabled. Then, let's go on to the output mode. When the pin is configured as an output, one of the modes, the push-pull or open drain, must be selected. The default is the push-pull mode. The push-pull or open drain mode selection depends on whether to activate the PMOS or not by configuring the corresponding register. If the PMOS is activated, the push-pull mode is selected, vice versa, the open drain mode is selected. We have already introduced that the push-pull mode is selected by turning on the PMOS. If the I/O is to be controlled as a high-level or low-level output, we can use the output control circuit to turn on the PMOS or NMOS. When the I/O is controlled to output a high level, the PMOS that connects to VDD or VDDIO is turned on, the current flows to the external devices and is called source current. When the I/O is controlled to output a low level, the NMOS that connects to VSS is turned on, the current flows from the external devices and is called sink current. That's how the push-pull mode works. When the open drain mode is selected, same as the push-pull mode, the NMOS that connects to VSS is turned on to output a low level. When the I/O is controlled to output a high level, as there is no PMOS, the pin will be floating. Therefore, an external pull-up resistor should be connected to VDD or VDDIO to provide a fixed voltage level. Note that the smaller the pull-up resistance, the faster the level shift speed, but the higher the power consumption. Then, we will introduce the HT32 MCU GPIO pin lock function. The GPIO pin lock function is mainly used to enhance the security and stability of the system by locking the configurations of specific I/O pins, to prevent system errors or external attacks from changing these critical configurations. The GPIO pin lock API can be used to lock the configurations of the specified I/O pins, which include the AFIO mode, pull-up and pull-down resistors, direction, driving current, etc., which cannot be changed until a reset event occurs. GPIO setting and application. Then, we'll introduce the GPIO clock. If PB1 needs to be configured as an input and PA1 needs to be configured as an output, the first step is to enable the clock. This is the program structure to enable the clock. The AFIO clock must be enabled as long as any pin-related peripheral is used. The AFIO is used to extend the peripheral functions of the pins. In addition, the corresponding GPIO port clock must be enabled according to the used GPIO port number. In this example, PB1 and PA1 are used, so the port B and port A clocks should be enabled. Then, configure PB1 as an input. First, configure the pin alternate function to GPIO using the AFIO GPX configuration function. The first and second parameters are the GPIO port and pin number. The third parameter is modified according to the alternative functions of different peripherals. If GPIO is used, this parameter is written with AFIO_fun_GPIO to switch the AFIO mode to GPIO. Then, use the GPIO pull resistor function to set the pin to pull up, pull down, or pull disable. In this example, it is set to pull down. Next, configure the GPIO direction to input and enable the input function. Now, the setting is finished. PB1, input mode, internal pull down, input enable. If PA1 is configured as an output, the push-pull mode is used by default. To use the open drain mode, use the GPIO open drain configuration function and set its third parameter to enable. This example configures PA1 as an output. The clock and AFIO have been set in the previous settings. Use the GPIO write-out bits function to configure the pin level to high or low. Then, configure the GPIO direction to output. Now, the setting is finished. PA1, output mode, open drain, output low. After the above configurations, the following will introduce how to use the input and output modes. The PB1 input level can be obtained using the GPIO read in bit function. Set means high level, reset means low level. Therefore, the input I/O state can be read to control the output I/O PA1 to output a high level or low level. This example demo is as follows. When PB1 inputs a high level, PA1 outputs a high level using the GPIO SetOut bits function. When PB1 input a low level, PA1 outputs a low level using the GPIO clearout bits function. This is the GPIO API table, which contains the GPIO driver API functions provided by the HT32 standard firmware library, and lists the relevant description and the corresponding GPIO registers. Holtec has a professional service team to assist in the development, design, and after-sales service. Welcome to contact our business unit for more detailed product information and consulting services.